Hello, I hope you're doing well and welcome to AliGorithm. In 1926, in a city called Moravia in Czechoslovakia, there was this guy called Mr. Borivka with his friend who's an electrical engineer called Mr. Saxel. They were discussing about problems, and there's Mr. Saxel who came up with his problem he faced in his job, that's the problem of electrical network design. At the first glance, the problem appeared to be easy for Mr. Borovka. I mean, you add a cable from the station to the city, and that's all. Now, suppose you have two villages next to the city. Well, you either may add a line directly from the station to the villages, but it costs a lot, and a cheaper solution is to extend the line from the city directly to the villages. So the problem can easily be solved here. Well, suppose you have this sophisticated network of cities, villages, renewable energy, nuclear energy, various source of energy, and you have to link them with the cities and villages. Well, the first solution is to easily add a cable alongside each road network. Even though it costs a lot, at least you ensure that they are connected as they were already connected with the road network. However, some lines you can easily eliminate, but other you cannot, as you may re-question the question of the connectivity of the electrical network. So here's the problem. You're trying to design an electrical network that goes alongside the road network that spans all of the nodes and that minimizes the total length or the cost. Well, mathematically speaking, we're trying to find a subgraph H of a graph G with the same set of vertices, but it minimizes the total cost of the edges of H. And here's the first theorem. H is a tree, where mathematically a tree is a graph that is connected and with no cycles. Well, first we see a graph that's not connected, where it's a set of trees, we call this a forest. On the right, we have a graph with a cycle, and in the middle, we have a tree. That's a graph with no cycle and connected. We can prove that we're looking for a tree as it should be connected, so it's not a forest, and it does not have a cycle. Suppose you have a cycle. Suppose, let's look for the cycle 1, 2, 3, for instance. Any edge from this cycle can be removed, and we can further improve the cost of our tree. And that's an introduction because we're looking for a minimum spanning tree. Hence, we're looking for a tree with minimum cost. So since we're looking for a tree that spans all of the edges with minimum cost, you call this minimum spanning tree, or MST as an abbreviation. Well, even though Mr. Borovka was the first to solve the problem, alternative and better solutions were proposed by Mr. Prim and Kruskal later on, who are the best and most famous algorithm for the MST. Today we're explaining Prim's algorithm. So Prim's algorithm, as shown on this grid, it starts with a vertex, no matter what vertex, starts building the MST incrementally. So you start with a vertex, no matter which one, and then you scan the edges incident to this vertex in yellow, and you add the one with the minimum cost to the MST in green. Now you have a new tree that's this single edge in green, and you scan the edges that are incidents to this new tree, and you add the one with the minimum cost to the new tree, and it became green. The algorithm continues like this until it covers all of the vertices of the graph. Now, to understand how Prim's algorithm works, let's consider this graph that presents the network presented in the introduction of this video. So it starts by a vertex, say A, and it scans the edges incidents to A that are AB, AE, and AD, and it adds the edge with the minimum cost, that's AD. So now your tree is AD. So now we start scanning the edges incident to this new tree that are AB, AE, and DB, DE, DH, and DG. The one with the minimum cost is DH, and it's added to the tree, etc., etc., until it covers all of the vertices of this graph. So in terms of pseudocode, the first intuition we have is that we start with any vertex. We build the MST incrementally by scanning the edges and getting the one with the minimum cost and add them to the tree. However, this intuition gives a bad complexity that's big O of V times E. However, this complexity can be improved with this min heap data structure, where in the min heap we can put all of the edges with respect to their cost, and then we pick up the one with the minimum cost, we add it to the tree if it suits our topology, etc., etc. And also this complexity bound can be further improved by replacing this edges min heap by vertices min heap, where the key represents the distance to the tree. That could be improved or updated each time a new edge is added to the MST. With the help of a data structure called Fibonacci heap, we can reach a complexity bound of big O of E plus V log V. So now that we presented the minimum spanning tree Prim's algorithm, let's prove that it works. I mean, we prove the correctness of this algorithm. Well, to do so, we use this lemma that's called the minimum cut property. What it says is that given a cut of this graph, that's splitting the graph into two sets, S and V minus S, the lemma says that an edge linking these two sets, or an edge of this cut with minimum cost, belongs to a minimum spanning tree of the graph. Let's present this lemma and show that it's correct. Well, suppose you have this cut and you have this S and V minus S, and consider an edge E that belongs to a minimum spanning tree, and suppose you have E star that's a minimum weight edge crossing the cut. Now let's try to replace E by E prime. This gives a new minimum spanning tree with cost less or equal to the old minimum spanning tree. Hence, E star belongs to a minimum spanning tree. Now let's use this lemma to prove the correctness of the Prim's MST algorithm. I mean, you start with a vertex. You already have a cut between this vertex and the rest of the graph, the one with the minimum cost by the min cut property. It belongs to the minimum spanning tree. You add it to this tree, and you do this by induction on the remaining vertices of the graph until all of them are covered. Finally, I'd like to point out something. The minimum spanning tree has a wide set of applications. Not only the electrical network design, the internet network design, the water design, supply chain, transportation network, and whatever you want, as long as you're trying to link vertices or entities with the minimum cost possible. But there is this nice application that I discovered by preparing this video that's the maze generation. I didn't know that we can use the minimum spanning tree to generate mazes. I mean, you can start by this table and then you build this connection graph where vertices are the cells that are connected by neighborhood where you can aim at opening some frontier or doors. You may also add a random edge cost to make the maze more random, and then by running a minimum spanning tree on this graph, you can open some doors, but you ensure that they are connected, so you can build this minimum spanning tree and this nice, well-looking mazes. Have fun! So this is everything for today. I hope you guys liked this video. If you do, please subscribe to my channel.